The prevailing belief among most scientists is that the theories regarding the universe's origins continue to be the primary explanation for the universe's early stages. This theory connects the formation of stars and planets, which eventually led to the development of life, including humanity itself. Despite its peculiar name, the Big Bang offers a detailed insight into what might have happened at the universe's inception. Initially, the universe was concentrated in an incredibly small space, much smaller than a pinhead, with particles densely packed. From this compact state, a massive release of energy and matter, referred to as the Big Bang, occurred. This cataclysmic event, which took place billions of years ago, set the universe's expansive history in motion. However, as scientific knowledge progresses, discrepancies have emerged, challenging the assumptions of this theory. When NASA launched the James Webb Space Telescope, JWST, the most advanced and largest space observatory ever created, experts expected its observations would confirm the Big Bang theory. Yet, within just 1 year of operation, the telescope astonished scientists with its unprecedented ability to peer into the distant past of the universe. The JWST's incredible capabilities have revealed galaxies dating back to a period so ancient that it challenges our understanding of the universe's beginnings. This revelation has sparked a wave of discussion about the potential existence of matter before the Big Bang. One particularly significant breakthrough occurred when cosmologist Rohan Natu, analyzing data from the telescope, discovered a galaxy from shortly after the Big Bang, marking it as the farthest galaxy observed to date. This discovery sent shockwaves through the scientific community, emphasizing the astonishing abilities of the James Webb Telescope. The massive potential of the telescope to reshape our understanding of the cosmos is just beginning to be realized, with promising revelations about the universe's earliest stages. This time period, which is loosely connected to prior cosmic history, holds the key to understanding the emergence of the first stars and galaxies. The discoveries made by the JWST have contradicted established theories, unveiling galaxies with characteristics that defy previous expectations. This surge of early galaxies has ignited a frenzy of scientific inquiry, pushing experts to reconcile these new findings with existing theories. As scientists continue to explore these revelations, they face fundamental questions about the very nature of the universe and the forces that guided its evolution. Beyond the clear advantages of the JWST, it is strategically located 1.5 million kilometers from Earth, shielded from interference and cooled to nearly absolute zero by its tennis court-sized sunshield. The telescope is equipped with a vast primary mirror and incredibly sensitive instruments, specifically designed to uncover secrets about the early universe that were previously hidden. This early cosmic period, known as the Great Dawn, took place approximately 200 to 300 million years after the Big Bang, marking the moment when the first stars and galaxies began to form. The process by which this unfolded remains an intense subject of research, with various theories being proposed, such as the roles of dark matter and dark energy or the interactions between star-forming gas and dust. The JWST's ability to observe galaxies from this era presents a unique opportunity for cosmologists to test existing models of the universe. By analyzing these ancient galaxies, scientists can either validate current models or identify gaps in our understanding that could lead to groundbreaking discoveries. Initially, the JWST was expected to detect only a handful of faint, small galaxies during its early studies. However, the reality far exceeded these expectations. The telescope's first images of the distant universe revealed an abundance of galaxies with diverse ages, sizes, and luminosities, far surpassing previous predictions. This unexpected flood of early galaxies has set off a race among space experts to redefine the records for the earliest known massive systems. New findings are emerging constantly, leaving even seasoned scientists in awe. Following the JWST's discoveries, both experts and the public have been eager to analyze the presence of these highly advanced early galaxies. Some theorists suggest that errors in how the telescope interprets large-scale observations might account for these astonishing findings. However, the consensus remains that these revelations represent a paradigm shift in how we perceive the early universe and provide an exciting glimpse into the potential for profound change in our understanding. The recent discoveries about early galaxies, made possible by the JWST, have raised significant questions about the universe's nature and challenged the assumptions of traditional cosmological models. While some experts are exploring whether these findings can be integrated into existing theories, others propose that these revelations might be the first signs of a universe that is far more complex and enigmatic than previously imagined. The critical question remains: how did the universe we know today emerge from the chaotic turmoil of its early stages? The JWST's early discoveries could dramatically reshape our understanding of the Big Bang and offer new insights, not only into distant galaxies and ancient cosmic structures but also into the very makeup of our own Milky Way galaxy. As Mark McFadden, senior scientist for science and exploration at the European Space Agency, aptly stated, "You build these machines not to confirm theories, but to break them. You simply have no clue how it will break." The origins of the JWST date back to 1985 at the Space Telescope Science Institute, STSCI, long before the launch of the Hubble Space Telescope. At that time, G. Weir, then the head of STSCI, was tasked with imagining what could come after Hubble. Despite initial doubts, Weir and a small team began laying the groundwork for what would eventually become the James Webb Space Telescope. Unlike Hubble, which primarily observes visible light, the JWST was designed to observe in the infrared spectrum, allowing it to peer deeper into the universe. This infrared capability is crucial for studying distant galaxies whose light has been stretched into the infrared due to the universe's expansion, making them invisible to telescopes like Hubble. With its large, cold, star-like mirror, the JWST became an essential tool for unlocking the mysteries of the Great Dawn. The necessity for the JWST became clear in 1995 when the Hubble Deep Field observation revealed a vast number of galaxies in a previously thought empty patch of sky. This discovery showcased the richness of the early universe and highlighted the need for a more powerful telescope capable of observing even further back in time. After years of development and an investment of around $1 billion, the JWST was launched on December 25, 2021. By July 2022, it was ready to begin its most critical year of scientific observations. Programs like the Early Release Science, ERS, and the General Observing Program were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded them. The JWST's observations have tested existing models of the early universe, revealing galaxies that challenge conventional cosmological assumptions. These extraordinary discoveries emphasize the importance of pushing the limits of scientific exploration and highlight the remarkable capabilities of advanced technologies like the James Webb Space Telescope. As researchers continue to analyze the data collected by the JWST, new insights may emerge that challenge and broaden our understanding of the universe. When the first data from the JWST began arriving, cosmologists eagerly awaited the results. Many scientists had been preparing their data analysis systems for this moment for years. Instead of following the traditional peer review process, which can take months, researchers opted to share their findings on preprint servers like AR14, where papers can be publicly accessed before peer review. This approach facilitated rapid feedback and discussions via online platforms like Twitter, where established scientists could quickly engage in dialogue about the findings. Rohan Natu described this new process as science by press release, and the subsequent surge of conversation was both intense and unprecedented. However, there were concerns about the potential drawbacks of this swift dissemination of results. Klaus Pontypool, a JWST project scientist at STSCI, cautioned that while the rapid sharing of results enabled quick communication and discussion, it also posed the risk of overwhelming the scientific process. The accelerated spread of discoveries, especially in such a groundbreaking mission, introduced challenges to traditional scientific workflows. Nonetheless, the general consensus among most experts is that the theory explaining the origin of the universe remains the cornerstone for understanding the early universe's phases. This hypothesis involves the creation of stars, planets, and life, including human life. Despite its odd name, the Big Bang provides a coherent explanation for the universe's beginnings. One of the most startling revelations came in early 2025 when the JWST detected an anomalous structure in a distant region of space, one that defied conventional explanations. At first, astronomers believed it was an early galaxy cluster, but upon closer examination, its spectral signatures didn't match anything previously recorded. The object emitted radiation patterns unlike those of stars, gas clouds, or even quasars. Some theorists proposed it could be a relic of an unknown cosmic phenomenon, possibly even a structure predating the Big Bang itself. Dr. Aisha Rahman, a leading astrophysicist at Caltech, proposed a daring hypothesis. What if the JWST had stumbled upon evidence of a previous cosmic cycle? According to a controversial theory known as the cosmic rebirth hypothesis, the universe might not have begun with a singular Big Bang but instead undergoes endless cycles of expansion and contraction. If true, this discovery could provide the first empirical evidence that our universe wasn't the first of its kind, but merely the latest in an infinite sequence of cosmic rebirths. Meanwhile, deep space physicist Dr. Elias Torvik at CERN argued another possibility. The JWST might have detected the effects of an alternate dimension intersecting with our own. According to string theory, additional spatial dimensions could exist beyond the three we experience, but they remain hidden because they are either too small or too weakly interacting with our universe. If JWST had indeed captured evidence of such an intersection, it could redefine our understanding of physics itself. The global scientific community was in an uproar. Conferences were held, research teams worked around the clock, and observatories worldwide pointed their instruments at the mysterious anomaly. Data poured in, yet every analysis seemed to deepen the enigma rather than solve it. Then, in mid-2026, the JWST made an even more shocking discovery: a series of light echoes, appearing as repeating bursts of radiation from deep within the anomaly. The pattern suggested a highly structured, almost rhythmic sequence, as if the cosmos itself was sending a message. Was this merely a natural phenomenon? Or had humanity, for the first time, glimpsed evidence of an unknown intelligence, one embedded within the very fabric of spacetime? This was no ordinary cosmic event. In nature, prime numbers rarely appear in random phenomena. They are often associated with intelligence, deliberate construction, or advanced computational patterns. Could the universe itself be trying to communicate? Or had JWST detected something far more profound? Perhaps the remnants of an ancient civilization that had mastered physics beyond human comprehension? Dr. Raman, Dr. Torvik, and an international team of researchers immediately launched an initiative to decipher the signals. They fed the radiation patterns into quantum algorithms, searching for structure or meaning hidden within. Days turned into weeks, and then, at last, the unthinkable happened. The patterns, when translated into binary code, formed what appeared to be a complex sequence of equations describing the fundamental forces of the universe but with variables and constants that didn't align with known physics. It was as if the message contained an expanded framework of the universe's laws, one that hinted at forces and dimensions humanity had yet to discover. At NASA headquarters, tensions ran high. Some feared that releasing this information to the public could cause mass hysteria, while others believed it was the most significant discovery in human history and must be shared. Meanwhile, agencies like SETI, CERN, and the ESA intensified their analyses, searching for independent confirmation of the anomaly's origins. Then, another twist shook the scientific world. As the JWST continued monitoring the anomaly, the rhythmic pulses changed. The pattern shifted slightly, almost as if responding to the analysis taking place on Earth. For the first time, a chilling possibility emerged. Was humanity merely observing this phenomenon? Or was someone, watching us back?